Hello, everybody. I'm very happy to have a research seminar today by Mr. Ziyin Liu. I want to briefly introduce Ziyin. So Ziyin is a graduate student in physics at the University of Tokyo. He studies in theoretical physics in the weather lab. Also, he's affiliated with the newly founded Institute for Physics of Intelligence. Currently, he is also working with preferred networks in Tokyo. In the past, he did the internship at Riken IP, and he also got a degree from CMU, and he was working for the natural language processing before. So currently, he is broadly interested in physics, statistics, and applied mathematics and machine learning. And recently, he has numerous publications in NeurIPS and HTMLs. So today, Ziyin will talk about stochastic gradient descent with multiplicative noise. So Ziyin, please start.
Thank you very much for your introduction. So today, my topic will be stochastic gradient descent with multiplicative noise. My name is Ziyin from the University of Tokyo. And this work is mainly based on our recent work, SGD may never escape saddle points. Just to warn you, I'm a physicist. So if you have a very mathematical question, I might not be able to answer you, but I will do my best. So what is SGD? Well, it is the main optimization algorithm for training neural networks. And other variants such as Adam and maybe other ones exist. And it is also used for other gradient-based models. And one crucial feature of SGD is its algorithmic simplicity. So what you do is that you basically take a subset of the training data, which we call the mini batch, and then you find the gradient with respect to this data. Mathematically, you can describe it with only two lines of equations. Here, W is the model parameter, and lambda is the learning rate. So our loss function usually look like this, taken as the expectation over the sampling of the data points. And then we compute the gradient with respect to a sampling of the loss function. And then we update the parameters. So here is a table of contents for this seminar. I will start with the background and related works, and then I will introduce our recent result that studies when SGD fails, and then I will end this seminar with some outlook comments. So what are the open questions? Well, a neural network is a highly nonlinear, non-convex function that contains many saddle points and local minima. Intuitively, SGD should be stuck in local minima very easily. So one question here would be, why does SGD work so well in practice? Also, it has been commonly observed that SGD work much better than gradient descent when training a neural network. So another crucial question here would be, why is SGD better than gradient descent? Also, it is often noticed that when the learning rate is large, the generalization is good. Importantly, an interesting intermediate learning rate regime exists. So when the learning rate is not vanishing nor divergent, you actually get quite good generalization behavior. So another crucial question would be, why does large learning rate help? So here is a figure taken from the Lukovic paper. You see that at small learning rate, the test accuracy is rather plateauish, but it features a very sort of fast increase to another plateau as you increase the learning rate, suggesting some sort of qualitative transition-like behavior here. So learning rate can also be crucial. So what are the current advances in this field? First of all, it is now widely believed that SGD helps with escaping sharp minimum. And a lot of works show that, including a work of mine. And also it is discovered that gradient descent with noise can help with escaping saddle points. Oh, sorry, there's a to-do. But there are a lot of classical works on this, and it's a very active area of research. The limitations of previous works is the reliance on strong assumptions. The most classical kind of works work on convex problems, but at this point, we're already quite sort of, the convex loss functions are quite well understood at this point. So the problem of dealing with neural networks has to do with how to deal with a non-convex landscape. And in such a setting, the following assumptions are usually made. For example, it is common to assume that the Hessian of the loss function is Lifshitz constant. Well, it has the Lifshitz property, well, meaning that the Hessian is bounded. And also a common condition is the PL condition, which implies that the only minimum in the landscape is the global minimum. Also more recently, there is this assumption called one-point strongly convex condition. So basically it says that the effective loss landscape is strongly convex after a convolution with the noise. So basically this condition sort of only works when your loss function is dominated by a strongly convex sort of background landscape, and you have sort of spiky perturbations that induces the saddle points. But this is also hardly the case for neural networks. Also, there is the correlated negative curvature. So this is that the gradient is correlated with the escape direction of a saddle point. Well, it sort of implies that you can already escape easily from a saddle point. So what are the challenges of sort of theoretically dealing with SGD? In my opinion, there are three. First of all, you have discrete time dynamics. Discrete time dynamics are known to lead to chaotic behaviors on a non-quadratic loss function. And those are very sort of hard to understand, unpredictable when you have chaos. And second, the special noise structure due to the mini batch sampling. So when you have mini batch sampling, the noise is both non-Gaussian and position dependent, meaning that the strength and the sort of the shape of the noise covariance matrix depend on the current model parameter W. And also there is the lack of the understanding of the loss landscape of a neural network in particular. Well, because, well, I mean, human beings in a way can only visualize sort of space landscapes in 3D. Well, and for higher dimensional spaces, it's very hard for us to sort of visualize and understand. So what does the loss landscape look like for an extremely high dimensional model, such as a neural network? This can also be a very important question. And in this work, we try to deal with all three aspects together and show that unexpected phenomena may happen. So now I'm ready to introduce the main topic of this seminar. So here's the problem setting. We'll be assuming a discrete time SGD, so the standard SGD algorithm. And there is mini batch noise due to random choice sampling. And we also consider fixed learning rate throughout training. So this agrees better with the practice of using the same learning rate for a considerable period of time. And it is also relevant for online learning, where it doesn't make too much sense to sort of change the learning rate, because you always get new data, right? And let us start with a warm-up example. Our results of this work are essentially more general variants of this example. So if we understand this example well, you basically sort of understand everything about this work. Let the loss function be like this. So W is the parameter and X is the data distribution. In particular, it's the input data. And X obeys this distribution, where X equal to 1 with probability 0.5 and X equal to -1 plus A with probability 0.5. when A is greater than 0, W equal to 0 is a local minimum. Very simple. And when A is smaller than 0, W equal to 0 is a local maximum. And we are interested in this case, where A is smaller than 0. So here's the loss function. And in this warm-up example, we let the learning rate be 1. And the goal is to escape from the saddle point, W equal to 0. So how fast does W escape in expectation? Well, exponentially fast. So if you do the calculation, you see that expected value of WT is equal to this term with an exponential rate of log of 1 minus A over 2. So that's the escape rate. However, what is the probability of escape? Well, it turns out that as t tends to infinity, the probability of escaping is 0. So you can basically write out the SGD dynamics, and you see that W of t plus 1 is 0 with probability 0.5, and it's equal to this value otherwise. Oh, sorry. And after t time steps, WT has at most t to the negative 2 to the negative t probability of being non-zero. And for infinite t, WT equal to 0 with probability 1. So even if your loss function is not a local minimum at W equal to 0, it converges to W equal to 0. So the message here is that SGD will converge to the local maximum with probability 1, even if its expectation escapes the local maximum exponentially fast. Well, the reason is that the single event that escapes so fast that it dominates the expectation, even though the probability that this event takes place is very small. And also, let me comment on the terminology. In this work, we say that a stationary point is a saddle point if it is not a local minimum. Okay, so you have 0 gradient, but it's not a local minimum. We say it's a saddle point. So this allows, so in this case, so in this sense, a local maximum is also a saddle point. And you can also discuss saddle point in 1 dimension, which is what we did. So this is a little abuse of the word saddle point. Okay, so the first main result is that SGD may converge to a local maximum. So this is a direct extension of the warm-up example to a wider range of learning rates. So the loss function is still this term. And with the same data distribution, then the SGD converges to the local maximum in probability if this condition is satisfied. Actually, it's actually not quite hard to satisfy this condition, as we will see in the numerical examples. So the message would be that it may be quite common for SGD to converge to a local maximum. And here are the numerical examples. We plot the histogram of the model parameter distribution over, I think, 1,000 runs, or maybe not, but over many runs. So here, the highest blue is the initialization. And the slightly darker blue is the distribution of the model parameter at step 10. And this spike is the asymptotic distribution of the model parameters. So we see that even though the underlying landscape is a local maximum, SGD actually converges to this maximum. And here is a slight variation of this example, where we added a 4th order term to the original loss function to make 2 local minima. And in this case, you still see that the SGD converges to the local maximums. And also, this example shows the range of where you sort of escape, which is plotted in white, and where you sort of converge to the local maximum, which is the color in dark blue. So note that there are 3 branches. Oh, well, so this plots whether the SGD escapes as a function of lambda, the learning rate, and A, which is which signifies the local curvature. When A is smaller than 0, as we discussed, we have the local maximum, right? So we mostly care about this half of the plane. And there are sort of three regions. The first region is the escape due to SGD instability at large step size. So you notice that even if A is larger than 0, you still escape. So that's a signature of the instability due to discrete timeness of SGD. And in this region, SGD is trapped. An orange line shows the sort of the theoretical inequality that we showed in the proposition. So it agrees exactly. And here is the escape due to vanishing noise. If you do the analysis sort of carefully, the strength of the noise of SGD sort of decreases as lambda squared. So when you have a sufficiently small lambda, the noise is sort of negligibly small. That's why you can sort of escape. We'll talk about the right figure later. So here is the second main result. SGD may escape saddle points arbitrarily slowly. So we have shown that when the learning rate is not appropriate, SGD may converge to a maximum. But what if we choose the learning rate appropriately? Well, the intuition is that the larger the learning rate, the easier the escape should be, i.e. the escape rate should increase monotonically with the learning rate. So before we state the result, let us first define the escape rate. So in our work, we defined the asymptotic average escape rate of W at learning rate lambda to be gamma of lambda as this term. Okay, and the optimal escape rate is defined as the supremum over all lambda. So it's the best possible escape rate. The escape is possible if and only if gamma is greater than 0. And if you have a negative gamma, that basically means that you are converging to the local maximum. And here the result, there are two results. First of all, assuming that the lambda is smaller than or equal to 1, if you have larger lambda, then basically you can escape sort of due to the instability, but that's sort of not something controllable and it's not desired. So we consider the case where lambda is smaller than or equal to 1 in this case. Okay, so there exists a differentiable loss function such that the SGD algorithm escapes the saddle point arbitrarily slowly, i.e. for any epsilon greater than 0, there exist loss functions such that the optimal escape rate is smaller than epsilon. Okay, and this is constructed by proposition 3, which is given here. The crucial point, well, the loss function is still the same as the warm-up example, and the data distribution is also the same. And you can calculate the optimal escape rate to be this value. And if you plot it, it's not a monotonic function, okay? So the message is that the escape rate is not a monotonically increasing function of the learning rate in general. So here is where the right figure comes into play. So these lines shows the escape rate, gamma, as a function of lambda. So you see that as you increase lambda, you first, in some region, the escape rate increases, but then it drops and even drops below 0. And that's the region where your SGD actually converge to the local maxima. And here's the third result, where we show that SGD may actually prefer sharp minima. So here is this old question. Why does SGD help? Well, it is commonly believed that SGD has some magical implicit regularization effect. And there are actually many mechanisms, people hypotheses, to be this implicit regularization effect, and it actually might be a compound effect. So there might not be a single cause, but the point is that people hypothesize SGD, the dynamics of SGD can help. So the dynamics of SGD may help select minima that are generalizable. For example, one mechanism is through preferring flat minima. So intuitively, flat minima are more robust to perturbations and are indeed good candidates for good generalizability. And some previous results include showing that the escape rate, well, from a sharp minimum, not the escape rate we just defined, but a different escape rate increases as the curvature increases, or maybe the escape rate increases as the learning rate increases. And in summary, it is believed that SGD prefers flat minimum. Okay, so before we state the result, let us first define the sharpness. Okay, so let W star be a local minimum of the loss function. Then the sharpness of W star is defined as S of W star, which is the trace of the Hessian at this point. And we say that a sharp minimum W1 star is sharper than W2 star if S of W star 1 is greater than S of W star of W2 star. Okay. And for an explicit construction, consider the following objective on a two-dimensional landscape. Okay. So you have fourth order term, and you have a term, only this term actually is data dependent through X, and the distribution of X is given by this probability. Okay. And you can compute the Hessian and find the 4 local minima of this example. So 2 of the local minima have a sharpness of 4, and 2 other local minima have a sharpness of 4 plus for A. So by controlling A, we can control the sharpness of this minima. And we will show that it is these 2 minima that SGD converges to. Okay.
Hi, Ziyin, I have one question.
Yes, please.
So in this definition, could you explain a bit more intuition of this definition? I say I don't understand well.
Oh, so first of all, because we have a local minimum, so all the eigenvalues of the Hessian are positive, right? And usually we say that a local minimum is sharper if sort of its how do I say, if its curvature is large, right? And
okay,
one additional possible sharp definition of sharpness is the determinant of the Hessian, but that's sort of equivalent. Well, for the problem we are trying to study, it's sort of equivalent to this definition. The point is that this sharpness increases monotonically as you increase the curvature of the local minimum. So that's the idea.
Okay, so if the eigenvalue is large, it's more sharp. So this part is I still don't understand.
Yeah. So we are basically saying that if the eigenvalue of the Hessian is large, then we say it's sharper.
Okay.
Yeah. It's actually a standard, commonly used in many related works.
Okay. So this is a pretty common way of definition of the sharpness of. Okay. Thanks.
But there are other definitions, but most of the definitions are actually equivalent to this definition in our setting. The point is that it is larger than the other 2 local minimum, and that holds for many kinds of definitions of sharpness. Okay,
thanks. So I have one additional question. So far, you are working for some special loss function.
Yes.
So do you plan to explain the case more like general like logistic loss or something else, or like you are just working on that loss function? I just wonder whether this discussion will be generalized to the general case.
Oh, very good question. So at the end, I will discuss a neural network example. So in that case, we will have a standard MSE loss, but no logistics loss or anything else. But we will have a minimal but realistic example to explain the relevance of the studied facts to deep learning.
Okay, got it. Thanks.
Thank you very much. So here is the numerical simulation for the example. So there are 2. So here is the initialization of the model parameters. And there are 4 local minima Okay. And you see that it converges to these two local minima, which are sharper, as predicted by the proposition. And here is our next result, which has to do with the non-convergence of adaptive gradient method. Well, here it's not, by non-convergence, I don't mean divergence. I only mean that it's not converging to a local minimum. So this section shows that what we have studied so far also apply to adaptive gradient methods. So Adam is known to have the convergence problem, such that it diverges on a sort of simple stochastic convex problem. Oh, sorry. And AMS grad is the proposed fix and is considered the convergent version of Adam. Okay, so it's defined as this, where G hat is the usual gradient, beta 1 is the hyperparameter, momentum hyperparameter, and M is the momentum. V is the preconditioner, and beta 2 is the preconditioner hyperparameter. And equation 15 takes the maximum of all preconditioners, and 16 is the update rule. Okay, so the crucial innovation of AMS grad is equation 15, which guarantees the convergence on a sort of a convex problem. And proposition 5 basically states that for a constrained optimization problem, if the learning rate is small, well, upper bounded by some value, then again, the loss function we studied in the warm-up example, AMS grad might not converge. Well, in particular, it will converge to a, in probability, to a local maximum. And also, it is worth remarking that the example we consider is actually similar to the original example in Reddy et al. 2018, which shows that Adam doesn't converge. So this is, in essence, the Reddy example, and this is our construction. And for this problem, the global minima has loss L equal to -1, and the global maxima has the loss L equal to 0. And the left figure shows what happens if we don't add momentum. Oh, well, for reference, we also show the performance of Adam and the performance of gradient descent. So when there is no momentum, both Adam and AMS grad converges to the local maximum, while gradient descent converges to the sort of the global minimum. And on the right, for completeness, we also show the case when there is momentum, well, equal to 0.9, which is the standard value. And you see that the AMS grad still converges to the local maximum. Adam sort of has a intermediate behavior here. It seems to have better property of escaping the saddle point than AMS grad, but it's not completely escaping in a way. And GD is sort of the same. So this shows that what we have studied is not sort of a unique feature of SGD, but also apply to adaptive gradient methods. Okay, so here is the final example of this seminar, and it also serves as a response to the question Makoto raised. So now we study a minimal neural network example. So what we actually study is a 2-layer neural network with one hidden neuron. So the network is defined as this, where W1 is our parameter and W2 is our parameter, and both are scalars. And the input is one-dimensional with a nonlinearity sigma. In our example, we set the nonlinearity to be quadratic. Okay, so it's x squared for an input of x. And the data set we use is also minimal. So we let x equal to 1 with probability 1. And the labels are either -1 or 2 with the equal probability. Okay, and the loss function is the mean squared error. And explicitly, you can write the loss as this. Okay. Well, one additional advantage of this example is that you can sort of find the global minimum and maximum easily and plot them. So here, the global minima are all the points that satisfy this relation with a loss of 2.25. And W1 equal to 0 are all the saddle points with L equal to 2.5. Okay. And despite the simplicity, it contains many features of a real problem. For example, there is inherent uncertainty in the data point, and there is a nonlinear network with more than one layer. And the global minimum is degenerate and has 0 eigenvalue in the Hessian. Okay. This frequently happens when you have an overparameterized network. And it's also sort of present in our minimal example. Moreover, common assumptions in theoretical works are violated in this example. For example, there is no Hessian Lifshitz property. Also, it violates the PL condition and the 1-point strongly convex condition. And for the saddle points, it doesn't satisfy the correlate negative curvature assumption. No, please read the paper for why they are sort of violated. For now, I will just state these as facts. So here is the numerical simulation. Here, this shows the loss landscape as a function of W1 and W2. Here, the 1 minus W2 kind of shape here are the global minimum. Okay, and here, this horizontal line is where W1 equal to 0, and those consist the saddle points. In particular, when the learning rate is small, in this case, it's 0.001, you see that the model parameters converge to the global minimum with some degree of fluctuation due to the mini batch sampling. And when you have a rather large learning rate equaling 0.1, you see that all the model parameters converge to the saddle point at 0, 0. Okay. And on the right, we study this problem in a more systematic way, where we plot the training loss as a function of the learning rate. So you see that when the learning rate is small, the model converges to the local minimum with a loss very close to 2.25. It's not slightly larger due to the fluctuation, but it's a sign that it's in the global minimum. And as you increase the learning rate, it sort of increases towards 2.5. And there is a range of learning rates where the model converges to a training loss of 2.5 before it sort of diverges suddenly. So this is the neural network example we study. Also, it has often been discovered that at convergence, there are some negative eigenvalues in the Hessian. Okay, and our work may actually offer an explanation here. So now we have finished presenting our main results, including SGD may converge to a local maximum, and SGD may take arbitrarily long to escape local minimum, and SGD may prefer sharper minima, and adaptive gradient methods may have the same problem. And now we will conclude this seminar with an outlook. So basically, the dynamics of SGD is highly complicated in a non-convex setting, and many unexpected phenomena may happen. And here are some future questions that I think are worth studying in the future. First of all, is it common for SGD to converge to saddle points in more realistic settings? So for example, are wider and deeper networks more likely to converge to saddle points? And how do we avoid converging to saddle points? For example, changing learning rates, batch size, inject noise, etc. may help, but convincing theoretical guarantee is lacking in a realistic setting. Also, is saddle points, local minima, necessarily bad things? Is there possibilities of benign saddle points and local maxima? For example, common practices such as early stopping ensures that we never reach the convergence regime of training. Is it possible that an early stopping point may correspond to a saddle point? Also, it's my personal thinking, the real brains are always dynamical and shows no sign of convergence. The brains that show little or no sign of adaptation often suffer severe cognitive diseases. So maybe general artificial intelligence should be the opposite of optimizational convergence. But it's just my humble opinion. Yeah. And that's the end. Thank you very much for your attention. And if you found my work interesting and would like to know more, please read our paper. Thank you very much. And please ask questions if you have any.
Thanks, Ziyin, for the nice talk. From the audience, do you have any questions? So maybe they might need to take some time to ask these questions. I have some questions. So based on this result, the conclusion is like, if you, so can you somehow like optimize the learning rate from this results? It's not possible. Still, it's too simple to optimize the learning rate.
Oh, you mean to find a sort of an optimal learning rate that helps you escape, or?
Yeah, exactly.
Well, that would sort of require you to know the exact landscape, right? And in practice, that's probably not something knowable except for very simple models.
Okay. I see. So in this sense, one of the contributions is that you find one particular example that neural network might fail.
Yeah.
So this is also one contribution, like the one.
Yeah, that's one message.
Okay. Oh, so actually there's questions.
I would like to comment that it's not a singular example in the sense that there are many other examples that might also exhibit the same behavior.
Okay, I see. So actually there's questions from in the chat box. Could you please respond?
First of all, thank you very much, Qibing, for asking this question. I wouldn't say SGD mostly finds the sharper local minima. It is still maybe the case that SGD mostly find flatter minima, actually, just that it's not preferring flatter minima sort of in a categorical sense. So the answer to the first question would be no. So actually, in my opinion, it still seems to favor flatter minima most of the cases. The answer to the second question, is sharper minima better from machine learning point of view? I do not think so. Intuitively, I agree with the standard intuition that flatter minima should generalize better because it's more robust to perturbations, right? So I would intuitively feel that flatter minima are better. But in my opinion, there is no really convincing example for the convincing theoretical argument for this in a realistic setting. Thank you very much. Okay, I see another question from Mr. Rutkowski. So the question is about the thought I have about brains. So the question is, do you think we could develop or use AI to diagnose such a human brain in trouble, such as dementia, Alzheimer's disease, etc.? I would say that would require us to know much better about our brain. And unfortunately, I'm not an expert in cognitive sciences. If we have really good models for how our brain should behave dynamically, then maybe the answer should be yes. But from my expertise, that doesn't include neuroscience, it's hard for me to answer. But I would say my answer is optimistic. I hope there would be such case. Oh, thank you very much. Okay, so I see another question from Mr. Tanimoto. So the question is, are these examples peculiar in terms of, for example, the low dimensionality that I considered? For example, when X and W are high dimensional, is it the case that the noise level varies so much? It is actually hard for me to answer. As I actually commented in the Outlook, it is actually, in my opinion, a very important future direction to study whether these examples carry over to more realistic settings where you have wider and deeper networks. But my opinion is that it may not be that peculiar in the sense that, as I have sort of cited in the work, it is often discovered empirically that at convergence, the Hessian of the neural networks, of realistic neural networks on real data, contain negative eigenvalues. So that would either imply you are not yet escaping from the local minimum, from the saddle points, or that would imply that you have actually converged to the local maxima, right? Well, to the local saddle points, right? So there are some sort of indirect evidences that even for realistic settings, you might actually converge to the saddle points instead of sort of escaping them in the asymptotic time limit. And in terms of the noise level, my opinion is that when you have a super small batch size, you will still get very high noise level that are position dependent. And if you have position dependent noise, you can have sort of quite wild behavior. And so, yeah, so it is not the case that in high dimension, you will have very small noise level, but if you have small batch size, you can still have significant noise. But if you have very large batch size, then I would expect the noise to behave Gaussian and rather stationary throughout training. Yeah, that's my answer to this question. Oh, I see another question from Madawa. I'm sorry. Here is the question about the opinion. What do you think about? What do you think of the opinion that every local minimum is a global minima in higher dimensions when deep learning is concerned? It is quite hard for me to answer this. From my understanding of the current literature, this idea is mostly about the case where the noise is negligible. For example, when you have gradient flow, so both the noise is negligible and when the learning rate is negligible, it does not seem, let me think. For overparameterized networks, I think it should be the case that every local minima is a global minima. Intuitively, I'm not too familiar with how people prove this, but the point is that you might not converge to the local minima, right? If you talk about the dynamics of SGD, then the SGD doesn't guarantee that you converge to such local minimum. My opinion is that if you consider the actual loss landscape, it might be the case that every local minimum is a global minima, but if you consider the effective loss landscape induced by SGD, this might not be the case. Well, in fact, it's the sort of the essential idea behind the 1 point strongly convex assumption, right? after the convolution, you have a strongly convex landscape. So the convolution with the noise would be crucial if you use SGD. And it is the sort of the landscape after involving with the noise that we should actually consider if we want to study SGD. That's my humble answer to this question. Thank you very much. I see another question from Wood. The question is, do higher order methods that use curvature information, such as the Newtons and natural gradient descent, address the issue of SGD? Well, actually, Newton methods are actually known to be attracted to saddle points, right? Because when you invert the Hessian, you actually make your gradient sort of attractive towards the saddle points. So when you use the vanilla Newton's method, you're actually attracted to the saddle points in a way. Regarding natural gradient descent, natural gradient descent, I think, is better than the Newton's method in this regard, because the preconditioner of the natural gradient descent is always positive semi-definite. So that might help you escape saddle points. I would wonder whether natural gradient descent always escape saddle points, but I'm not sure of any proof so far, but it's a possibility. I think it's a possibility. And therefore, it's a very potential, worthy future direction to study, I think. Thank you very much.
Okay, from the audience, do you have any further questions? Okay, seems like we have a lot of questions at this talk. It's very nice. Okay, so thank you again for your great talk, and let's thank the speaker again.
Thank you very much.